Hello, welcome to chapter 5 in ADS, and here I'm going to dive deeper into harmonic balance and various ways I can use it to design power amplifier, right? So this is a chapter 5 in ADS. And as for the libraries, I'm going to use a demo kit, and I'm going to set up the resolution at the start itself because I had that checked. So it says resolution is that. Let's say finish. Once I'm done with this, I have an empty workspace, and I'm going to very quickly create a small signal tuned stage. So I'm going to say new schematic and say SS tuned. Okay, and then this is for the this is for your Wi-Fi 6E. So it will be from 5.85 to 7.15. Okay, so that's what it is. And I'm going to very quickly create the meshed stage under small signal. Okay, so to do that, all I need to do is I'm going to use a FAT1 and F5. I'll move it here. I operate it from I will operate it from 5 volts or 4 volts, sorry. So let's go ahead and put here slight what you call source degeneration. So using lumped components ideal, I'll put some source degeneration here for stability, and I'm gonna do this as 230 pico, 230 pico. So there are two what you'll say, there are two back vias. Okay, and I will quickly create a decoupling. Right, so I'm going to use one of their inbuilt inductors, right, from the demo kit. So let's look for an inductor. Okay, and this inductor, I'm going to let this be the default value which shows up because I'll include this in tuning. So let's just copy this. Copy. Okay, that's the one for copy. Okay, and I will just show you how to do a small signal followed by a large signal tune. Okay. Okay, and then I need bypass caps, and these caps don't go much higher in values, right? So maximum they can go to 2.3 picofarad, I guess. So I'll use two of them, or one will also suffice. Yes, this is, so let's just copy this one. Okay, and then they will go through a via to ground, and via is not properly modeled in this kit, so we will later model this via in EM. Okay, and then I am going to have the supply voltages here, sources, frequency domain, and from my previous learning I am biasing at minus 0.85, and this one at 4. Okay, so this is my bias. I can also look at the currents, so I can put in a probe component in here. So if you go to probe components, and then whatever direction anticipated, you are going to mirror accordingly. Call this as IDS. Okay, this is for the biasing, and then I'm going to match it, so I'm going to use these two capacitors for coupling here. Okay, and then I'm going to focus in my at my center frequency first. So I'm just going to put here termination as term 1 and term 2. Okay, and then I just put include file, and then S parameter simulation file, S parameter controller, and here I'm going to look in band, which is from my 5.85 to 7.15. And 0.1. Okay, so that's my S parameters, and then I'm going to put in here the load stability and the source stability circles, right? And then I'm just going to hit simulate. Okay, once done, I'm going to look at S11 and then S22. Okay, they are over here. They need to be matched to the center. Let's also look at the source stability and load stability circles. Source stability and load stability circles. Okay, and I'm going to put here a auto scale of 1. Sorry. Okay, so they are crossing over here. So I'm going to add a certain feedback over here, or I can increase these. Let's see if this is going to help me get rid of those. Okay, not much. So I'm going to put here A. If you remember, I was working with what is called the low frequency stabilization. So I used to put a resistor here because this gate doesn't draw any current, so I can do that. So I will go to the demo components. Okay, so I'll look at resistance. So this resistance is 100 ohms. This is hardly going to change anything in terms of RF response between input and output because it's in the DC line. So it just moves them out. Right, that's one thing. And let's make this 320, 320. Okay, see, almost out, but still not out all the way. So here what I'm going to do is I'm going to add another form of feedback which is called lead compensation. Okay, so I'm going to put here a resistor which is 800 ohms, let's say. And 0.2 picofarad, which is going to be a mem cap here, which is going to be 0.25. Okay, so they are all out. Don't worry about this line because this line is just joining the endpoints in case of a I haven't given this any scale, right? So if I just go it and give it certain scale, let's say 1.2. Okay, so these are joining the last or end points. So you do not try to stabilize this. This is not instability. Okay, one is over here, other one is over here, S1 is over here. So one way is I can put in a series inductor in here, a very small inductor, right? So I'll just copy this one. From where do I do a copy here? Then I'm gonna rotate it, place it over here, and simulate this. So it's moving closer. Okay, this one I can move up. So to move up, I would need a shunt inductor, right? So I'm going to choose this one, copy it out. Okay, so this I want to use a ideal one, not ideal one, but a real one. So I'm going to copy this one. And just rotate it out. Okay, obviously I don't need this, so I'll put here 1. So roughly that works. Or I can put 1.5. Okay. Okay, so it's close, and I want this one to be close. So one way is I can use a shunt cap and a series inductor. Other way is I can use a series inductor and a shunt cap. Now I can go this way. I'll put a shunt inductor and a series cap. So I'll just use a shunt inductor. So this has moved over here, and then I can use a shunt. So I can use 3 turns. Okay. And then I can use a shunt cap, a series cap, sorry. So let me just move everything to the side, and I can use a series cap. So I'll just copy this one. How do I copy this? Here, over on this side, and I'm going to hit simulate. Okay, so little less, so 2.5 turns, and a smaller cap. So I want like 1.8 picofarad or 1.6 picofarad. Okay, coming closer. Let's bring it further closer. Okay, and over here, okay, so let's look at the matching. So if I go here, I can put here S21. Okay, so there is a 0.6 dB variation on the gain here across band for a small signal. And if I look at S11 and S22, they are better than 12 maybe. Okay, so they are better than 12. And this, I want to tune it for power, so I'm not going to use this noise figure and all that. So what I'm going to do now is I am going to convert this into a symbol, right? So I will just copy this. So I'll just go here and make a copy of this cell, and I'll call this cell is LS tune, last signal tuned. So next thing I'm going to do is last signal tune. Okay, so now that is being done, and I am going to modify this. So I am going to just remove everything other than the circuit, So I have moved everything other than the circuit. So I'll put in pins P in, P out, VDD, and VGG. Okay, so we are done with this. So let me create a quickly a symbol for this. So let me just put it on the side to make a symbol for this one. So I'm going to take 1, 2, 3, 1, 2, and 3. Okay, so I have got P in. Sorry. Why does it look symmetric? No. Then I have P out. And then I have got VGG. And then I have got VDD. Okay, so that's my PA. Single stage. Right. So the next thing I'm going to do with this stage is I'm going to look at the large signal performance of this. Okay, so what I'll do is I am going to open an example project. So let's look for an example project. Open example. And here I am going to go to simulation examples, go to HV examples, and go to large signal amplifier simulation, this one. And then I'm going to unarchive it. Once I have unarchived, this is going to open. So it has opened here, and my interest lies in stability versus frequency versus power, this one. So I'm going to go back to my example recent workspaces, go back to my chapter 5. Here I'm going to go to manage libraries, and under manage libraries I'm going to add a path. Add a path to that example project. So that will be over here. It is called large signal something, right? L large signal. And over here I am going to add this lib.def, and here you see I have all this. So I am interested in this one, say copy cell, and I am going to copy it to my library and keep the name the same and say OK. Now here you don't see the data display windows, so I have to go from outside from Windows, and here I am going to go to the folder, which is probably over here as large signal amplifier, and here you will see stability versus frequency versus power. That's the data display window. I'll just say copy, and then I will go back to my, which is chapter 5 in ADS, and here I'm going to paste this. Okay, done. So we are almost done. So now what I'll do is I am going to okay, so I'm going to just go to manage libraries and then remove the link to this example and say close. And now I have the schematic, but here it is not hierarchically copied, so basically this is not there. We will put our own stuff in here. So one of the supplies is over here, which I will call as VDD, and I will create one variable called VDD, right? So let me just make a copy of this again for VGG. VGG I'm going to keep fixed as 0.85 minus, it's a depletion mode device, and then I'm going to bring in my large signal tune, which is not yet large signal tune, but I'm going to do a large signal tune here. Okay, so this is my PA under consideration here, and this is the device under test. Okay, so I have thrown out the example PA and I have placed mine, and here M sub would be replaced by your include file here, right? And this, all this information I can keep aside. Here, as far as the excitation, I am going leave the default here, but then I am going to change that over here. So it says start, stop, step, and these are the frequencies. So let's say I want to do 5.85, right? So 5850 and 7.15, right? So I will do a 7150. Okay, so this gap is how much? This gap is 850, 150 over here, 1000. So basically, just want to find out the half point. Okay, so 7150 minus 5850 equal to this divided by 2. So what? Didn't do a divide by 4. Okay, that doesn't matter. 650. So 650 megahertz is my, so these are going to be 3 frequency points, the 2 edges and the mid band, and then I'm going to do a sweep from -10 to, let's say, +10 steps of, let's say, 0.5. Okay, so we are done with that. So let me explain to you briefly what this is. This has got 2 ideal couplers on the 2 sides, and what it's trying to do is large signal on the input side. So it puts in a large signal tone and then looks at the reflection. So reflection comes as B1. Okay, so whatever, so basically the incident power, okay, and this is B1 is the reflection, right? Let me just open the data display, or rather simulate it and then explain it in data display what that is. Okay, undefined VDD, sorry about that. So I'll just put a variable here. VDD is equal to 0.4 volts. VDD equal to 4 volts. Okay, and I might need a probe component in here. So let's go to the probe components. And here, let me just mirror this and put this here is ID. Put this as ID. Okay, then. So let's hit the simulate. Okay, so what's happening, I'll explain here. Okay, so what it says is S11 is B1 by A1. Okay, so incident power to the, sorry, reflected power to the incident power. Okay, and then A2 by HB B2 by A1. B2 by A1 is the gain. Then B2, so you can see here it's a hybrid simulation. What it is doing is it is putting in large signal at the input and small signal at the output, and they are slightly offset in frequency, so I know which one is what, and then I am computing the reflection coefficients here. So here, what's wrong here is delta 1, because delta is now being used maybe as a determinant inbuilt. So that is gone. So now this is all there. So what am I looking at? I'm looking at across the input power, what is happening to the gain, what is happening to the gain across frequency and across power. So I'm looking at across frequency and across power, and here I'm looking at what you call large signal stability factor, K, which is being computed here, right? So K better than 1 means that it is stable. And here I'm looking at S22 reflection on the output side, and I can have an equivalent of this over here, and here I can say permute S11. So this would be basically looking at the input side. Okay, so the input return loss is better than 10 across frequency across power. Same is for the output. Now let's say if I want to, how much compressed this is. Okay, so this is 11.5, so 10.5, that's 1 dB compression, right? So let's look at what happens to the impedances. Okay, so this over here, M1 is at the power of minus 10, and this is a power of plus 10. Okay, so they are far apart. I need to get the frequency wise, I need to get them closer, right? I need to get them closer frequency wise. And S11 is over here, so I can push this S11 up. Okay, so let's try to look inside. So push that up means I can increase this. Okay, so they have moved up, and over here they are spread a lot. So I want to bring them closer. To bring them closer, cannot blindly do it. So the impedance here, I can do a broadband equivalent of that, and they will come closer. Okay, so I want to see what this whole thing looks like. This whole thing is my match, isn't it? Okay, so this is my output match. I want to see what this output match looks like, and then do a broadband, right? So I can copy these, edit, copy, and then I will make a new schematic. It's a load. New schematic, I'll say load network. Say Control V. So let me see what that 50 ohm looks like. So I will put here the termination of 50. So simulation S parameter. I'm going to look what this termination of 50 looks like at the center frequency, which is going to be 6.5 gigahertz, right? So I'll simulate this at 6.5 gigahertz. Simulation S parameters, S parameter controller. So I'm going to look at single point 6.5. Correct. So just for that namesake, and I'm going to hit simulate. Okay, and I'm going to look at S11. Okay, it's over here. There's no question of broadbanding. This is already nearby, right? Okay, hang on a second. Okay, so in this case I can do one more thing. I can reduce these points to like 2.5, and then there are 3 points in here, and let me put a tune. Let's see if it will allow me to do that. Let's go to this guy, and that, and steps of that, that's fine. That, 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 correct, and maybe little of this, little of that, 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 this one, and this one. Okay, so I have all the components which are here for tune, because I didn't see an obvious reason for this spread. In case of real PTKs, it won't be spreading like that. Okay, so let's focus on that. And where is our tuner? Over here. Correct. So now we are going to look at the output capacitance over here. So that's what it is doing. So it's over here. Then there is a shunt inductor, which is this one, which I can increase. Okay, and this capacitance I can increase to bring it up, right? And this is 3, 2.75 is correct. And then let me see how much is the effect of this one on the spread. So this is 320. This is source degeneration, right? This is your feedback. This is your input side. So for that I have to bring in my input into question, which is over here, and I can do many things with the input. So this is coming closer. So okay, so this one you won't be able to do more than 2.3. I'll have to put 2 capacitors in this case, and this one is that matching. Okay, 7.5 is centered. Okay, and let me also put this on current. So that's the current part of it. And let's see what is the impact of biasing. Okay, I understood. Okay, so I have biased it up. Okay, let's go back to this one, the output side, which is over here. This is not to be varied, this one. Okay, so I'm going to say update, say close. Obviously there may be a violation and the maximum value is low. So what you're seeing here is across power, across frequency, and this one is kind of, this one is referring to 5.8 and this is 7 point something, right? So let's see what is the spread over here. So there is a dB of spread roughly, and over here it's compressed by 0.5. How much is it compressed by? 12, 11, 1. Okay, so I'll put this figure versus output power, right? Control C, Control V. So I'm used to seeing it versus output power, right? So here versus output power. So this is what I need to look at. Control C, cancel, delete. I'm going to look at S21, add versus in dB versus the output power, which is HBB2, and in dBm, and here I'm going to look at B2 fundamental. Okay, so the same curve is versus output power here, and let me put here a marker. Okay, so here we are looking at 11.3 and here we are looking at 10.3. so let's put two markers here, one marker over here and another marker over here. So I'm looking at 11.3, 10.3, 11.8, 10.7, and 12.2, 11.2, 10.2. so this is compressing much harder, the top one. Okay, so the idea is very simple. You want to match under power and make sure your stability looks okay and your lateral losses are better than 12, right? So let's say this is the scenario and I accept this PA. Okay, so this is last single tune. Now you can also do what you call the load pull, right? So before this, let me also plot efficiency numbers here, right? So efficiencies are not computed here, right? So so what's the difference between computing over here versus computing in the data display window? So what happens is, if you want to change, if you want to have different data sets and you want to apply the same formulas, you will not be able to do that if you write the equations in data display window. So had you written these equations in your measurement equations, then what will happen is that whenever you change they change something, for example here, and store it to a different data set, right? So all these computed values will be available here. Okay, so you have, whenever you run the simulation, it will compute and give you here. But when you do in data display window post simulation, then for every data set you will have to recreate it, or you cannot, or you have to, when you change the data set over here, these equations will apply to new data set. But if you want to compare the two data sets, then you'll not be able to compare them because these equations are valid only for the default data set. So there is a difference between writing the equations here where if you want to compare two data sets, then these equations should not be written here. They should be written over here. So I can basically just go and copy these equations on this side. That will also work, right? Now what do I want to do? Okay, so I want to write the equations for efficiency. I can write the equations here, but then as I told you, it should be written on the schematic using measurement equations. So I can say the DC power PDC will be equal to magnitude of VDD multiplied by ID dot I, and look at the zero component of this. Okay, so there's a issue here, so you need to go here and see what's the problem. Is a VDD available here? HBIDI. Okay, so that's what it is available. Is VDD available over here? Okay, HB dot. So as I told you, this is a mixed mode simulation. Okay, hang on a second. HB IDI, isn't it? Okay, now VDD is not available. Okay, so VDD is not available, right? So what you can do is you can go here and make the VDD available. It should be, right? So it should be HB.VDD. Let me try that. No. SM.VDD. No. VDD is not available at all. Okay. So in this case, what you can do is you can force this VDD to be appearing. So if you go to Harmonic Balance and go to output, and then you can add VDD. Why don't I see VDD here? Yes, add. Okay, now it will be forced to output VDD, and the simulation is done. So let's see if VDD is available now. Kind of strange. Here it is available. So what's the problem here now? Okay, so that VDD is available. So now this is your DC power. It would be, I can plot that. So the DC power drawn goes up like that, right? And then the output power, so I can write the equation for the output power. So I can say input power, for example, and what am I sweeping here? RF power, right? So HB RF power, this I'm sweeping. Okay, so this is in dBm to watts. So I can convert this to watt. And if I plot here P in, so P in is over here, I can put it on the right side axis. And there are three traces which are overlapping because it is doing 3 times, but it's doing the same value. So this is your P in. And then the next thing which I want to look at is P out. Okay, P out is equal to dBm to watts, and here it will be HB dot your B2, right? So that's your output power, and I'm going to look at fundamental. So that's your output power. Okay, y should be a complex number. dBm 2 watts. Y should be a complex number. It should not be a complex number. It should just be a plain watt. P out. What happened to my P out? Why do I get this over here? Oh, is this dBm? P out is in dB, right? This is in dBm. Okay, so something is crazy here. So let's do that. So had this been dBm, okay. Okay, so DC power is way over here. And the output power is way over here. So let's see what happened to the efficiency now. So I'm putting in 10 DC power. I'm putting out as 10 milliwatt, 4 milliwatt. Okay, so the efficiency is 4%, so 40%, sorry. So I have got PAE. PAE is equal to P out divided by P in plus PDC into 100. That's PAE. And let's plot PAE. Equation PAE. Okay, so the PAE is around 40%, right? Okay, so let's see what is special a load pull will do on this, right? So I have a stage here and I want to expose this to a load pull. And I want to explore whether I can further improve it. My inputs are tuned, my outputs at large signal are tuned to 50. So what good is the load pull here? I want to see that, right? So let's see that. And if I want to do the gain, okay, let's put here S21 dB is the gain, right? So equation S21 in dB is the gain. Okay, so that's the gain and that's the efficiency, right? And at 1 dB compression point, I'll see the efficiencies. Okay, fine. Okay, so what I want to do is at this output power, I want to see how much is the load pull effect. Now, here the load pull has to be done at a constant output power. So basically the gain has to be bumped up so that it delivers the same power. Otherwise efficiency has no meaning. It has to be specified at a given output power, not a given input power, right? So that's how, let's see how in the example a load pull is implemented. Okay, so I'm going to close this. I have already unarchived the load pull example, but still I will go ahead and show you. So you can go to file and say close workspace, and let's say open example, and under HB load for load pull. Here is the load pull. Say next. What is this tick mark? Directory already exists. Say next. Okay, so I already have it, so you understand where it is coming from. So anyways, so I'm going to go back to my workspace, and here I want to attach and I want to copy that load pull example. So I am going to copy. So I'm going to manage libraries, add, and I will go here and look for load pull. And load pull. So I'll go and add this load pull. Close. So you see, this is a constant power delivered. Okay, so this would make sense. Okay, so this is at a constant output power. So doing load put for a constant input power has no meaning, right? Because you are comparing apple to oranges, right? So constant output power is what I want. Okay, so I'm going to copy cell. Okay, constant power delivered, and here I'm going to copy to my library and say okay. So it's copied. Then I am going from outside, going to load pull, and here constant power delivered. I'm going to copy that into my chapter 5. So I'm going to paste it over here. Okay, so now I am ready to detach this. So I'll go to manage libraries and detach this and say close. So now here I have that. Let's open that. Okay, so I don't want this. I don't want all this stuff. I need to put my PA in here and try to understand what these formulas are and stuff like that, right? Okay, and see how I can make it usable for my own. Okay, so I'm going to remove all this stuff. Okay, so we are all set. Okay, so now I can put in my PA here and then the include file, right? So I can bring in my PA. So which is going to be this one. Right? And we'll connect the biases. And low is minus, so let's check what our low was. So when we were doing stability versus frequency versus power, this is 0.67 and this is 4. So that's 0.67. So low is 0.67. So you have to look for where that variable is. Low is minus 0.67 minus 0.671. Okay, so that's there, and high is your 4 volts, correct? And RF frequency I'm going to do here is 6 point, hang on a second. Okay, so the frequency is set to 6.5 gigahertz, right? So I am going to do this load pull, and I am going to set the source frequency, a source impedance, ZS. So let me see where this ZS is coming from. So this is for sweeping, sweep 3 is for sweeping S11. Sweep Again, this is S11. So these are the two dimensions. Okay, so here this is for the load, but why is it calling it S11 center? It should call S22, right? Isn't it? And if I double click it, okay, so here it's just the naming convention, I guess, because it's not S11, it's the load, right? It's to do the tuner, right? So with the tuner, load tuner S11, right? And this S11 I have to compute, so that's why it is called S11. Okay, so load tuner, I'm going to sweep X and Y in a circle, right? So this is the row of that for the load pull. So I'm going to, let's say, do this as 7 or 8. Okay, and let's center this on 0 0. That's basically going to be the center of the Smith chart. So that's the center of the Smith chart, right? And I want, let's say, 100 points. Okay, so then it will divide 100 into rows and columns, right? Okay, so that would be over, some would be in here, it's not there. So basically it is sweeping in parameter sweeps. Okay, so it's doing in parameter sweeps here. This is how it's doing it, right? And imaginary, real, imaginary. Why there are two harmonic balances here? Trying to understand what these guys are trying to do. One is over here, other one is over here. So in example, you have two harmonic balances. Is it not going to be a problem? And second thing, why this is not 50? Why ZS will not be at 50? So I will make this ZS also at Z0. Right. And why there are two harmonic balances? This harmonic balance is doing a sweep. Understood. Lines, number of points. This harmonic balance is not doing anything. It is. There is a stop there. And there is nothing for sweep. So I think somebody was working on this and they just left it. So this was not correct. So they just left it. And here this will be called HB1. Okay, it's already in use. Just don't want to mess this up in case they are using it. I don't think they should be using two HBs. So let me just make a new schematic and just place that over here and delete them from there. So that's okay, so that I can recover it. So here now it can be made HP1. So we are already doing a sweep here, right? Okay, so let's hit simulate. Okay, so the issue is this is not the model. I have to have my include file. So that's done. And here I should be able to now run the load pull on, see what happens. So it does it. Everything is empty. No analysis found for parameter sweep 3, parameter sweep. Oh, so parameter sweep 3 is referring to HB1, parameter sweep for optimization, and sweep 2. So this is your nesting. Okay, let's run this again. Okay, nothing comes up, so it's basically broken down. Why is it broken down right in the equations? Okay, let's put back what it was. Okay, so that we have a case. Your stuff is not working, so let's just copy this and put it back here. Let's enable this, so let's make this one as HB2 as it was. Uh, already in use. Okay, so this will be HB1 and that will be HB2. So let's make it HB3 for now. Let's enable this one, put here back HB1 and put here back HB2, and parameter sweep 3, which is over here, was referring to HB2. Let's see if they were working with this. Is a complete project. Okay, so it does something, but still outputs are not there. So I think I didn't change anything other than some values for your sweeps. I didn't change anything with the harmonic balance settings. And did it come up with the warning? Okay, the regular warnings are there. It says it has done this, and it has written into this file, which is over here, and then this doesn't show up because in the equations things don't show up. is high, is underscore high. So basically it seems like it has broken down, right? So their example has broken down. Now let's see if it is not a constant delivered power. Let's see with the input power, because this is quite complicated. So I'm not sure if this was working to start with. So I can go to example project and see if it's working for them. So what I can do is I can go to ADS, I can say close the solution and go to their load pull example. So go to their load pull example, and here I am going to look at the constant this, and I'm going to hit simulate without any changes. So here I didn't do anything to it. So basically their example project is not working. I can see it's not working, right? So somebody hasn't figured out these equations to be right, and they just packaged it and just shipped it with different versions of ADS, and it's not working. So basically this is not working. So let's copy another one. Okay, so I'm gonna just close this workspace, and I am going to my chapter 5. Okay, and it was not working. So let's go to okay, let's go to again attach the workspace. So manage libraries and go to this and go to load pull. Go to load pull, and over here attach the simplest one, which is this HB1 tone load pull, and just say copy cell and copy cell to this library. That's okay. HB1 load pull, I have to copy that from here. Okay, So if I go to load pull, HB1 load pull, right? So that's the one, right? HB1 tone load pull. So I'll just say copy, and I will copy it to chapter 5. So, and then paste. Okay, so now I'll go back to my solution and go to manage libraries and disconnect this one. Close. So now I have got HB1 load pull. I'm not sure if this one works. So I am going to, I don't want this. I want to put in my include file, which is over here. Then the next thing is I'm going to delete these. Okay, delete these v in. So I'm not deleting any of their labels, so you cannot blame me for this not working. Okay, so they have a power measurement block here, which we do by writing equations. But anyways, this looks a much simpler this thing. So let's put in here our PA. So this is a large signal tuned PA. Okay, so this is kind of connected, and here I have to specify the biases. V low is minus 0.67, minus 0.671, and this is going to be 4 volts, and this is going to be how many megahertz? 6500 megahertz, and fundamental I'm going to put as 50, and here I am going to put this at 00, which is the center. Okay, so having done that, I'm all set. So here I'm putting in 10 dBm of power. So we are not doing sweeping the power and then optimizing the output delivered power and then looking at the load pull at a constant delivered power. This is quite complicated, and they didn't, they have an example which doesn't work, right? So let's see if this one works. So 10 dBm in, and this circle has gone to the center now because this has become 0 and that has become 0.75, 150. So let's just run this. Okay, so this one works. So now what did I do? I basically said that I large signal tuned it, and I did a load pull, and I'm looking at P delivered contours and PAE contours, and I see that they are very much where I expect them to be. So what is the proof? What am I trying to prove? What I'm trying to prove, okay, so 11 dB gain, so 10 dB, 11 and 1 dB compression is 10, at that efficiency is 45, roughly 40 what we had, right? So what I'm trying to prove here is, if you do a large signal tune, so let's just get this out of the way. So this is what I'm trying to prove, which, the more experienced guys in PA, they won't agree with me at the face value. So let's look at this. Okay, so what I'm trying to prove here is this schematic which you have given in your example allows me to look at the output impedance across power. And what did I do? I tuned the match to be good at the compression, right? So basically what did I do? I tuned, looking at the match, I tuned it to be best for the under compression. The match has to be the best one, right? And then I did a random number crunching through your another example, which is over here. This is your random number crunching. And with this random number crunching, you came up with your P delivered and PAE contours, which are right on top of 50 ohm. So is this not a computational overkill? Rather than using this schematic, which was very simple and give a more intuition to what was happening to the load match. Okay, here in load pull, you were blindly crunching your numbers here, right? And you arrived at the same results by a brute force, versus you were intelligently matching your impedances under compression over here, like this, matching under compression, and you will get the contours on the 50 ohm, right? There's no question of load pull giving me the impedance where I should be tuning. So blind and brute force versus intelligent. I leave it to the audience or users of ADS and also the employees of or the field application engineers of Keysight. Okay, you have two examples. Can you tell me the difference between this one and that one in terms of goal you are trying to accomplish? This one I am doing the output match under compression and making sure that it is well matched under compression. And this one I'm blindly crunching the numbers, though I'm reaching the same result over here and same result over here and over here. So my question to Keysight guys is, why would I go to do something blindly when I have insight into what's going on? And then my question is to Maury and Focus. Why do you make a load pull stand in the first place if you can have this setup in the lab, which is not difficult to do? Okay, it is not difficult to do. You can have such setup in the lab. Okay, so what's the point of spending 300 or 400,000 or $800,000 in doing a load pull and a source pull when you can do this in, like, a couple of $1,000 in the lab? So you try to explain me this, and why the load pull is so important for a PA designers. That's my question to all the big PA designers, right? The more seasoned ones. That why would I do this simulation, not this simulation? So I'm going to stop here. Okay, I will wait for an answer from anybody who is willing to answer.